Time for power. Okay, so yesterday we talked about work, and work was equal to a force dotted with the displacement. So that was F dot delta x, or sometimes written as F dot d, which is Fx cosine theta. There's that cosine component in there. What we're talking about today, though, is the extension of that. Power. Because when we have power, which we designate with a capital P, this power is just the rate of doing work. And a few small notes about all of this. When we're talking about power here, this is a capital P, not to be confused with pressure. Pressure is also a capital P, but if you're using pressure, then you're not talking about power. Okay, and as likewise, if you're talking about power, you're in a different realm of pressure. But note that while this is an uppercase P, a capital P, it is also not momentum. Momentum was a lowercase p, and it was a vector. It had an arrow over the top of it. Power does not. Power is a scalar. Now, since it is a rate of doing work, anytime we see this word rate, we should be thinking divide by time. If we asked, hey, what's your pay rate? You'd say some amount of dollars per hour. It's something per time. So when we say the rate of doing work, it is some work divided by time. And we can also think about this as the rate of using energy. Okay, so both of these are power. So we can think about it in terms of work or in terms of energy. Like, how much power does your computer use? Mathematically speaking, we define power then as a work divided by a time. It is thus the rate of doing work. But a really cool thing we can also do with this is we know from yesterday in the prior video that work is equal to a force dotted with a displacement. And if that force is in the same direction as the displacement, so if the force is going to the right and the displacement is going to the right, then we know that the angle between those two vectors is 0. Cosine of 0 degrees is equal to 1. So if we wanted to, we could say that this work could just become Fx. Technically, there's a cosine term there, but if cosine is just equal to 1 in this case, we can just kind of ignore it. Now, if we look at this F delta x over t, a force times a displacement divided by a time, we actually see something interesting with this displacement divided by a time. This is actually one of the first things we saw when we talked about motion in the world of physics. Displacement is measured in meters. Time is in seconds. Meters per second is nothing more than a velocity. So we can say that while power is a work divided by a time, we can also think of it as a force acting on an object with some velocity. That is also a definition of power. Technically, there could be a cosine term in there if it was acting at a weird angle, but let's just ignore that for now. We're not going to use this derived definition very often. We're going to kind of stay over here with the work divided by time. That's a more useful form of that equation. But if you wanted to, you could derive from that the power equation equals a force by a velocity. Now, in terms of units, the English units of power are a little weird, because the English units of work were a foot-pound, and then now we're dividing that by a second, which you have probably never in your life seen the unit of foot-pounds per second. But there is a unit of power that you're probably very familiar with, especially if you're into cars. I'm talking about horsepower. And you have to say horsepower in a very cool way. Because if you don't say horsepower in a cool way, then nobody will really know if you're talking about horsepower or if you're talking about something else. When we talk about horsepower, we can actually go back into history and learn where this term of horsepower came from. 1 horsepower is equivalent to 550 foot-pounds per second. And the reason why this entire unit of the horsepower was even created was because of mining systems. Back in the day, we didn't have cars on the street, so you couldn't roll up to your friend and roll down the window and say, "Hey, how much horsepower do you have in that car?" You just couldn't do it. What you did have were mining systems, and specifically around here in Western PA, we had a lot of coal that were, and still, mining. But at these plants, at these mining facilities, they would use horses to draw water out of the mines. Basically, you get a horse, you get it to walk in a circle all day, you put that up with some mechanical systems, and you can lift water with a bucket. Ta-da! Or with a Archimedes screw. This, however, is rather annoying. While you might love horses, you have to feed horses, and you have to brush them, and you have to give them carrots. And if Cinnamon the horse needs reshoeing, you gotta reshoe that horse. And you hope that Cinnamon the horse lives a nice, healthy, long life, because if that horse dies at some point in time, then you've run out of a horse. And now you gotta buy yourself another horse. On the other hand, a mechanical engine, you just fill it up with gas. And then, it destroys the environment 100 years later. But at that point in time, it's a great thing to have engines over horses. The only issue is that if I'm a mine owner and I've got 6 horses working in my mine, how many engines do I actually need? Well, when this was being talked about and thrown about, whenever the salesmen for these engines went to the mine owners, they made an equivalency. They said, look, this engine is equivalent to this many horses. It has this much horsepower. And the coolest word ever in existence was born. Okay? On average, a horse can put out around 550 foot-pounds per second. What if the horse had an off day? Well, Joe, then it'd be a little lower. But on average, for most draft horses, you're getting about 550 foot-pounds per second. We'll call this 1 horsepower. And thus, our unit exists. Nowadays, in our cars, nice muscle cars, nice road cars, they're kicking 500, 600 horsepower, which is a lot. My little sedans are kicking somewhere around like 180 horsepower. But it is what it is. In the SI units, though, much better units in my opinion, because they don't damage my throat, we have watts. W-A-T-T. Not a football player, or players at this point in time, but named after James Watt, who did a lot of stuff with electricity, believe it or not. This is why you will often see, what is the wattage of that piece of equipment? How many watts are being used by your computer? Maybe whenever your graphics card spins up, it's using more watts, it's drawing more power whenever you go to play your video games or whatnot. That is the same idea. But this is more of an electrics point that we think about it for, but we do use it often. If we didn't want to use the watt, which is abbreviated with a capital W, we could say this is joules per second, because it is simply work per time. It's also important to recognize that this capital W here, that is a unit of watts. It is not work. Work is also a capital W. Oh boy. So please be careful about that. If you're writing that W and it comes after the number there and you have finished out a problem, it is a unit there of power. It is watts. If it's into an equation like work equals F dot X, then you have a work. So please be careful about that. Okay? In our next little bit, we're going to take a look at how to actually look at work and power in some problems. But until then, you all take it easy. Adios. And goodbye.